Hello, my name is Emma Dimming from Team More 11, and there's nothing I'm more passionate about than robotics. I joined the team in freshman year and instantly fell in love with the atmosphere. The older kids were always busy and focused. They all knew exactly what had to be done in order to complete the robot, and I wanted to be a part of that. I wanted to work with the team in order to create something amazing. What's nice about our robot is that we are one of the only schools that have two teams competing. When I joined freshman year, I was part of our all-freshman team that was created in order to get freshmen more involved on the robot and allow them to learn more about what's going on. Starting out, I worked on mechanical sub-team and was chosen to be on drive team, and we made it all the way to finals in Worlds that year. If you had told me at the beginning of that season that I would later be design lead my senior year, I wouldn't have believed you. Yet, robotics introduced me to so many new people and brought me so outside of my shell that I was able to become a completely new person. This year, our robot is made up of 5 main mechanisms. First, the ball is taken in through the intake. There, mechanism wheels are on the outside of the hex shaft in order to center the ball. What's unique about our intake is the custom 3D printed mount that holds together the piston, metal bar, and polycarb. We decided to use polycarb because of how much flex it gives us. Anytime we are hit by another robot, the polycarb will flex and then go back into place. On the same mechanism as our intake is the hopper. This polycarb bin helps us take balls straight from the human player station and allows us to carry multiple balls at the same time before they go through the feeder. In order to avoid jamming in our feeder, we have a V mechanism. The wheels on either side of the small ramp spin in opposite directions, so one pushes balls away while the other one pulls balls through. This allows us to only take in one ball at a time instead of allowing multiple balls to go through and get jammed. The V mechanism feeds right into our feeder, which is composed of 10 belts and 20 pulleys. We used a belt system not only for aesthetic, but also because we wanted to keep a consistent compression on the ball as it was passing through. There are 2 stages for the feeder, the bottom and the top. Each stage is run by one motor with a 12-to-1 reduction, and a figure-8 tube allows the belt to run in opposite directions and make the ball travel up. From there, the ball is fed into our shooter. Our shooter is composed of 2 Coulson wheels and a 4-inch solid aluminum inertia wheel. That wheel alone weighs about 5 pounds, and it is there because as each ball is shot, we want to keep the momentum of the hex shaft the same in order to get a consistent shot. So, making the hex shaft have a larger inertia will make it slow down less in between shots because it will have more resistance to change. This shooter is run by 2 Neos with a 3-to-2 ratio, so we only need to run it at about 50% power to get more consistent shots, and programming has more leeway in using their PID to put the percentage up or down between shots to allow the hex shaft to spin the same speed so that the balls are shot at the same velocity. We as a team decided to go for 2 shots, one from behind the trench and one from right under the goal. In order to get these 2 shots, we have a piston on top of the shooter that activates whether we want the hood up or down. Right now, we are in the process of making our final shooter, where the triangle on the side will actually work in locking the piston so that it extends further than the hood and cannot flex back. The final mechanism is our elevator, used for climbing at the end of the match. We made our carabiner completely mechanical, so once the elevator goes up, the carabiner can drop down on the bar and rotate when the elevator drops so that it locks on. In order to ensure that the robot would not fall during a match, a bicycle disc brake is attached to the side of the elevator and activated by a small piston. Our team's robot would not look as good as it does right now if it weren't for teamwork. Our team is made up of 2 categories, tech and non-tech. The non-tech side has chairman's, business, and media sub-teams, and the tech side has design, mechanical, electrical, CNC, and programming. Without all of these sub-teams, our teams would not run as smoothly as it does. Non-tech sets up outreach events for us to bring in new members and spread the message of FIRST throughout our community. They bring in sponsors for us so that we can afford to build such a complex machine, and they keep our sponsors up to date with YouTube channel and social media accounts. The tech side would not be able to manufacture our robot without working with one another so closely. Mechanical creates prototypes for design to work off of, and from there, design is able to put together a full robot. Parts are given to CNC to be cut, mechanical to be put together, electrical to be wired, and programming to be coded. Each sub-team works hand in hand with one another and trusts each other to complete the task given to them so that the next sub-team can get to work too. As the lead on the design team, I took a different approach with my team this year. In the past, the lead did everything and rarely let other team members on design participate in the design and the components of the robot. I knew that I would be spreading myself too thin if I were the only one designing, and I would not be able to give 100% to the entire robot. To avoid this, the robot was split up the most I've ever seen it. Every mechanism that I had previously explained was designed by a different student. I was able to delegate different tasks to the students that I knew were best suited to carry them out. Teamwork helped us to design a well-functioning robot that would not be as good as it is if all of the work relied solely on me.